Hello friends, let's continue with another problem on sampling in which we shall compare the two forms of sampling theorem, namely the low-pass sampling theorem and the bandpass sampling theorem. The sampling theorem that we have seen already is known as the low-pass sampling theorem. Recall what it states. It says that if we have a band limited signal, band limited to W hertz, say this is the signal which is band limited to W hertz, then the signal can be perfectly reconstructed from its samples if the sampling rate Fs is greater than or equal to 2 times W. Now in this case, this signal happens to be a low pass signal. Now, what do we mean by a low pass signal? A low pass signal is one whose spectrum includes the zero frequency. But the band limited signal in general can also be a band pass signal, which does not include the zero frequency. Suppose this is our band pass signal with maximum frequency W. As per the sampling theorem, if the sampling rate Fs is greater than 2 times this W, then it is possible to recover the signal perfectly from its samples. So this form of sampling theorem is known as low pass sampling theorem because it only takes care of the maximum frequency contained in the band limited signal. It doesn't take care of what is the minimum frequency or what is the bandwidth of the signal. However, another variant of the sampling theorem called the bandpass sampling theorem considers the bandwidth of the signal as well. According to bandpass sampling theorem, it is possible to perfectly reconstruct the signal from its samples even if the sampling rate Fs is less than 2W for some specific sampling rates which is captured in the statement of the bandpass sampling theorem. So let us look at the statement of the theorem and compare it with the low-pass sampling theorem, and then we'll look at the problem. As already stated, the low-pass sampling theorem states that a band-limited signal, which can be a low-pass or band-pass signal, band-limited to W hertz, can be perfectly recovered from its samples if the samples are taken at a rate Fs greater than equal to 2W hertz. As per bandpass sampling theorem, a bandpass signal of bandwidth B hertz and maximum frequency W hertz can be recovered from its samples by bandpass filtering if the sampling rate is 2W by K, where K is the largest integer not exceeding W by B. That is, K is the floor function of W by B. All hard sampling rates are not necessarily usable unless they exceed 2W as per low-pass sampling theorem. Let us understand it. So in this case, as given, the bandwidth of this bandpass signal is B hertz. That is, suppose the lowest frequency is W1 hertz. So the bandwidth B is equal to W minus W1. The largest frequency is W hertz. Then if the sampling rate Fs is equal to 2 times W upon some integer K. Now, what is K? K is given by the floor function of W by B. Let us recall what we mean by a floor function. Suppose 4.3. What is the floor of 4.3? It is 4. The largest integer not exceeding 4. So it is 4. Say 4.9. What is the floor of 4.9? It is again 4. Because the largest integer not exceeding 4.9 is 4. Compare it to the ceiling function. Suppose if we have 4.3 and want to take its ceiling. Ceiling is the smallest integer greater than the number. So what is the smallest integer greater than 4.3? It is 5. What is the ceiling of 4.9? That is again 5. Okay, so you can see that floor and ceiling functions are different from round off function, in which if we are rounding off 4.3 to the nearest integer, it will be 4 and 4.9 will be 5. Here in the definition, we use the floor function. I hope it is clear. So with this, now let us look at the problem. So the given signal is m of t equal to 10 cos 2000 pi t cos 8000 pi t. There are two parts of the problem. Part A, what is the minimum sampling rate based on the low-pass uniform sampling theorem? And we have to repeat this part for bandpass sampling theorem. There is a term used here, uniform sampling. So the sampling that we have seen is uniform sampling, because in that the samples that we take, they are uniformly spaced. So this is 0, this is TS, this is 2 TS, and so on. So the gap is TS between two successive samples, and that is what we mean by uniform sampling. Look at the problem. M of t equal to 10 cos 2000 pi t cos 8000 pi t. Now here we can use the formula twice cos A cos B equal to cos of A plus B plus cos of A minus B, and accordingly we get here 5 times cos 10,000, 2000 plus 8000 is 10,000 pi t plus 8000 minus 2000 is 6000. So cos 6000 pi t. Now this is of the form cos 2 pi f1t. So from here f1 is equal to 5000 hertz, and similarly from here f2 is equal to 3000 hertz. What is W? The maximum frequency. It is the maximum of f1 comma f2, which is maximum of 5000 comma 3000, which is 5000 hertz. So as per low-pass sampling theorem, the sampling rate must exceed 2 times W, and therefore the minimum sampling rate required, so Fs min is equal to 2W, which is equal to 2 into 5000 equal to 10,000 hertz or samples per second. So this is part A of the problem. For part B of the problem, the minimum sampling rate Fs min for part B as per bandpass sampling theorem is equal to 2W by K, where K is the floor of W by. So what is the bandwidth of the signal here? B is equal to, as per our notation we used here, the maximum frequency is W and minimum is W1. So for this problem, maximum frequency is 5000 and minimum is 3000. So 5000 minus 3000 equal to 2000 hertz is the bandwidth. So what is K? K is equal to floor of W. What is W? W is the maximum frequency, which is 5000 upon the bandwidth B, which is 2000, and that is equal to floor of 2.5, and floor of 2.5 is 2. So accordingly, the minimum frequency required for sampling as per bandpass sampling theorem is equal to 2W by K, which is equal to 2 into 5000 by 2, which is equal to 5000 samples per second. So we see here that it is indeed possible to sample at a rate less than 2W, and still we can perfectly reconstruct the signal using bandpass filtering. However, note that the sampling rate in this case should be exactly 5000 samples per second. Not all other values between 5000 and 10,000 in this example will be workable. However, if the sampling rate exceeds 10,000 samples per second, then as per low-pass sampling theorem, we can still reconstruct the signal. So I hope this part is clear to you. Thank you very much.